Hello, this is a geometry video. It is chapter 5, section 4, and today we'll be talking about indirect proof. And we already don't like proof writing as it is, so indirect proof can be kind of tricky, but hopefully we'll smooth it all out for you so it's not as bad as you think. So first, before we start with indirect proof, we want to kind of revisit what a direct proof is versus an indirect proof. So in a direct proof, which is, by the way, what we've been doing in the past, is where you have a true hypothesis. So when you're proving something, it's generally like an if-then statement. So you have a true hypothesis, and then you prove that the conclusion is true. It's pretty straightforward. But an indirect proof is just that it doesn't directly go to the point. It actually gets there in a roundabout kind of way. Another way that we refer to an indirect proof is what we call a proof by contradiction. And so what you do in an indirect proof is you start by assuming that the conclusion is false. So whatever they're telling you to prove, you actually start by assuming that it's false. And then after you assume that it's false, you basically prove that that said assumption is false. And if that assumption is false, then by contradiction, the original conclusion must have been true in the first place. That might sound kind of confusing, so I want to go to some steps on how to do this before we get to the examples. But like I said, I'll explain how this works in the examples. So here are the steps for how to write an indirect proof. Number one, identify the conclusion to prove. So you have to know what they're asking you to prove in the first place. Once you know that, you assume that that conclusion is false by assuming that the opposite is true. Okay, so for example, if it says x is greater than 5, then you would start by proving or by assuming that x is not greater than 5, so it would be less than or equal to 5. Something like that. So you assume that it's false. That's the first thing you do. Then in step 2, and I want to emphasize the word logical here, use logical reasoning to show the assumption leads to a contradiction of the hypothesis. Now, a contradiction can be a contradiction of a definition, a contradiction of a postulate, a theorem, or a corollary. So you want to find a contradiction, and once you find that contradiction, you state that since the assumption led to a contradiction, then the original conclusion must have been true. So again, that it sounds easier said than done. So here's an example. We're going to get started by not doing a full-blown proof yet, but start getting some practice on how we make that assumption. Because remember, the first step is to make that assumption that is false. So here's my conditional for part A. It says if 6 is a factor of n, so there's my hypothesis. If 6 is a factor of n, then 2 is a factor of n. This is my conclusion.
Jason Kwan, please go to the ESL classroom immediately to meet Mrs. Nab. Jason Kwan, please go to the ESL classroom right now.
Thank you, Shannon, for that lovely interruption in my video. Anywho, so here's my conclusion. 2 is a factor of n. And so remember that the first step in an indirect proof is to state that the conclusion, or assume that the conclusion is false. So if it says here that 2 is a factor of n, then that means that I'm going to assume that that's false, and if that's false, it means that the opposite of this is true. So my answer for part A is that 2 is not a factor of n. So if I were going to prove this, I would start by assuming that 2 is not a factor of n, and then proceeding. So again, we're not going to do the proof right now just yet. Right now we're just learning how to get this assumption down first. So part B says that angle 3 is an obtuse angle. So that's my conclusion, that angle 3 is an obtuse angle. So I need to assume that the opposite is true. So if angle 3 is not an obtuse angle, so angle 3 is not an obtuse angle, which would mean that angle 3 would either be a right angle, or it could be an acute angle, as long as it's not an obtuse angle. All right, so now you can try do it yourself. And remember, all we want right here is state the assumption necessary to start the indirect proof. We're not actually going to prove it just yet. Okay, so that's the first step that you're going to be doing. And now in example 2, we're actually going to show you how an indirect proof works in its entirety. It says here, write an indirect proof to show that if 3x plus 4 is greater than 16. So there's my hypothesis. Then x is less than negative 4 is my conclusion. So we have hypothesis, conclusion. Okay, so basically your given is the hypothesis and the conclusion is the part that you want to prove. So I've kind of already done that part for you. And then remember that our first step with our proof, and you don't have to do it like in a 2-column style, it's more like in a paragraph style, but we are going to first assume the opposite of what we're trying to prove. So if we're trying to prove that x is less than negative 4, I'm going to say that x is the opposite of being less than negative 4, which would be that it's greater than or equal to negative 4. Now in this case, we can actually use a t-table to help us with this little guy. So I'm going to put different values of x here, and I'm going to put the expression negative 3x plus 4 over here. And what I'm going to do is, because I'm assuming that x is larger than or equal to negative 4, I'm going to pick x values that are larger than or equal to negative 4, starting with negative 4. Negative 2 is larger than negative 4, 0 is larger than negative 4, and so is 3. So I've picked a sample of numbers, negatives, 0, and positives, that happen to be larger than or equal to negative 4. And I plug them into my expression here. So negative 3 times negative 4 is positive 12, which is 16. And then here, negative 3 times negative 2 is positive 6 plus 4, which is 10. And then negative 3 times 0 is 0 plus 4, which is 4. And then negative 3 times 3 is negative 9 plus 4, which is negative 5. All right? Now what we can see here is that all of these values that we're getting are actually less than or equal to 16. This is equal to 16. These numbers here are all less than 16. All right? So that's basically a contradiction, because that's a contradiction because the given was that negative 3x plus 4 was larger than 16. Okay? So now that we've contradicted that, it means, therefore, since using numbers that were greater than or equal to negative 4 led to a contradiction, it means that x greater than or equal to negative 4 is actually false. And if x greater than or equal to negative 4 is false, it means that the original conclusion must be true, which is that x is less than negative 4, not greater than or equal to negative 4. So this must be true, and that's your proof. There's your Helmholtz, and that's an indirect proof for you. So now I want you to try do-it-yourself number 2, both A and B. I've already kind of gotten started for you, and then we'll move on to another indirect proof. All right, so here we have Javier, or Xavier, asked his friend Christopher the cost of his meal and his date's meal when he went to dinner for prom. Christopher could not remember the individual costs, but he did remember that the total bill, not including tip, was over $60. Use indirect reasoning to show that at least one of the meals cost more than $30. So basically what we're going to do here is write an indirect proof and what we know. So the easiest thing to do is to basically kind of create some variables. So I'm going to go ahead and say that X is Christopher's meal, which we don't know the price of. And Y is going to represent his date's meal, which we also don't know the price of. But what we do know, the given, is that the combination of the meals, like both of the meals together, so the cost of X plus the cost of Y, was over $60, so greater than 60. And what they want us to prove, it says that to show that at least one of the meals, so at least means or, so either X is greater than 30, so remember X is Christopher's meal, so either Christopher's meal was more than $30 or his date's meal was more than $30. Now remember that with an or statement, you only have to prove one of those in order for this to work. So there you go. Now we're going to start with the assumption. Remember the first thing we want to do is assume that our conclusion is actually false. So if x is not greater than 30, then it would be that we're going to assume that x is less than or equal to 30. Or if y is not greater than 30, then y is less than or equal to 30. Alrighty? Now if that's the case, we're going to use logical reasoning. We already know from the given that x plus y is greater than 60. If I replace x and y, let me, I don't want to do that yet. If I replace x and y with what they're representing here, if x is less than or equal to 30, I'm going to get 30 plus 30, which is now 60. All right? So I'll get x plus y is less than or equal to 30 plus 30, which is less than or equal to 60. It's another way of looking at it. So all I'm doing here is I have my combination of the two meals together, and if x is less than or equal to 30, and y is less than or equal to 30, I'm replacing x and y with 30 here. If I add those together, I get 60. So now what I have is a statement that reads x plus y is less than or equal to 60. Well, this expression is a direct contradiction of the given, which is that x plus y is greater than 60. So that contradicts, and you can see how our goal is always to find a contradiction. So that's a contradiction right there. And since it contradicts our given statement, then that means that this is false. X is not greater than or equal to 30, y is not greater than or equal to 30. So therefore, if that's false, then the original conclusion must be true. So x is greater than 30 or y is greater than 30. And that's your proof. Real easy peasy Japanesey. Okay, so now I want you to try do it yourself number 3. And then I think we're going to go on to our next example. And here we go. This one's going to be a little bit trickier, so hopefully you'll follow along. It says, write an indirect proof to show that if x plus 2 is an even integer. So here is our hypothesis. If x plus 2 is an even integer, then x is an even integer. So here is my conclusion. And so I've already gone ahead and written down the given and the proof. And so we start with an assumption. And it says here, I'm supposed to be proving that x is an even integer. So I always want to start assuming the opposite of that. So if x is not an even integer, then obviously x is an odd integer. And that's where things get funky. So we have to have some way of representing what an odd integer would look like. So what we're going to say is that if it's an odd integer, what makes a number odd is that you have an oddball. Like, for example, you can always pair up the numbers. And then, like for example, 5 is odd, 1, 2, 3, 4, 5. You can put groups of 2. Those are pairs. And then you always have this oddball of 1. So hopefully that makes sense when you see that this is the expression that we want to use to represent an odd integer. 2k plus 1. The 2 represents the pairs. So you can have any number of pairs. K is an integer. So for example, with the 5, you could go 2 times 2 is 4 plus 1. If you wanted to find 7, 7 could be written as 2 times 3 plus 1. So this is your pairs. And then you always have a plus 1 because that's what makes it odd, is that extra plus 1 there. So this is going to be our expression that represents an odd integer. And so now we're going to use some algebra to kind of do the rest of the proof. We want to use logical reasoning here. So in our given, what we're going to do is we have this x plus 2 right here, right? So we're going to take x plus 2 is an even integer. We're trying to see if x plus 2 is an even integer. But we're going to start by assuming that it's an odd integer, that x is an odd integer. So if x is an odd integer, it means that I can replace this x with this expression. So I'm going to get Let's do that in black. Okay, so what I'm doing now is I'm replacing the x here with 2k plus 1, and then I'm adding the 2 because of the plus 2. Okay, which means that if I want, I can actually invert these two. The order in which I add doesn't matter. So that means that I can write 2k plus 2 plus 1. And if I do that, it means that I can take this expression here and factor out the 2, because they both have a 2. So 2 times k is 2k, 2 times 1 is 2. So same thing, so now I have 2 times k plus 1 is plus 1. So we know from the beginning that that k is an integer, okay? This number right here, k is an integer. So the fact that I have k plus 1 here means that it's still an integer. For example, if k was 7, adding a 1 to 7 is not going to change the fact that it's still an integer. So k is an integer and k plus 1 is an integer. So I could say, for the ease of things, that m equals k plus 1. And if m equals k plus 1, that's an integer. I can replace this with m, which will give me 2m plus 1. Now, why would I want to do that? Because I want this number to have the same form as this number. 2k plus 1, 2m plus 1 basically means 2 times an integer plus 1. Now, why did I want to do that? Because I know this is odd. Writing a number in this form means it's odd. And since this number is in the same form, it means that this number is also odd. So x plus 2 is odd. But that's a contradiction. Because we just said at the beginning of the proof, given that x plus 2 is an even integer. So now we have assumed that the conclusion was false by making the x an odd integer. We did some algebra and have now shown that x plus 2 is also going to be odd, which is a direct contradiction at the beginning. So now if this is a contradiction, then it must mean that x was not an odd integer, that in fact x was an even integer, and therefore you've proved indirectly what you wanted to prove. So now if you will try this example on your own, I will move on to the last example, which is this guy right here. And this is not going to be too complicated, but it does require us to have two cases. This is basically the triangle exterior angle theorem. It says, if an angle is an exterior angle of a triangle, prove that its measure is greater than the measure of either of its corresponding remote interior angles. We've already had this theorem in the past. So angle 4 is supposed to be bigger than angle 1, and it's supposed to be bigger than angle 2. So what I've done over here is I've kind of translated that into my given. Given that angle 4 is an exterior angle of triangle ABC, they want us to show or prove that the measurement of angle 4 is larger than the measurement of angle 1, and that the measurement of angle 4 is greater than the measurement of angle 2. Now in this case you have an and, so you can't get away with only proving one of them. So again, we're going to start by assuming the opposite of this statement. So the opposite of this statement is that the measurement of angle 4 is not greater than, but less than or equal to the measurement of angle 1, or that the measurement of angle 4 is not greater than, but less than or equal to the measurement of angle 2. Okay? So the opposite of the and statement is an or statement, and the opposite of greater than is less than or equal to in both cases. Now, because this is an or statement, we only need to prove one of them. So we're going to go with this guy right here. I'm sorry, I don't know why I just said that. That's not true. We're going to prove both of them, because it originally was an and, so we want to prove both cases. All right, we're going to do it just like that. We're going to have case 1, caso número 1, and case 2, caso número 2. In case 1, we are going to say that the measurement of angle 4 is equal to the measurement of angle 1. So we're going to go ahead and go with this guy right here. And we're going to prove this guy. Remember, again, it's an or statement, so I'm sorry I keep confusing that for you. But an or statement means we only have to prove either this guy or that guy. But this guy has two pieces to it. It's less than and it's equal to. So here I'm going to do the equal to, and over here I'm going to do the less than. Like that. Okay? Case one's actually the easier one. So we know already from the exterior angle theorem that the sum of the two remote interior angles of the triangle is equal to the exterior angle. So we know this in this scenario. We know that the measurement of angle 4 is going to equal the measurement of angle 1 plus the measurement of angle 2. And since we know from this point here that 4 and 1 are the same thing, we can actually replace angle 1 with the measurement of angle 4 plus the measurement of angle 2. I'm recording. So now what's going to happen is we're going to solve, and by subtracting the measurement of angle 4 from each side, you're going to end up with 0 equals the measurement of angle 2. Well, that's a contradiction, because an angle measure is not an angle measure unless its angle is at least greater than 0. So you can't have an angle measure that is either negative or 0. So 0 equals the measurement of angle 2 is a contradiction. So we're good with that one, contradiction. And now we're going to go to case 2. And in a similar fashion, we still know that the measurement of angle 4 is equal to the measurement of angle 1 plus the measurement of angle 2. And the definition of an inequality states that if you have something that is equivalent to the sum of two things, then obviously the angle 4 has to be larger than any one of these by itself. You might remember that in a different video we talked about how if you have two people that have, for example, we could say, I don't remember the names that I used last time, but let's say we've got Joe is over here and Joe has $50. And then this is like, I don't know, Tom and Mick. And so Tom and Mick combined have $50. So basically Joe has the same amount of money as Mick and Tom combined. That means that Joe has more money than Mick and Joe has more money than Tom because combined they equal him. So that's just the definition of an inequality. It's part of the properties of inequality. So based on that, we know that the measurement of angle 4 has to be bigger than the measurement of angle 1. But that again is a contradiction because it says here that the measurement of angle 4 is less than the measurement of angle 1. And so now we have another contradiction. And since both of those led to a contradiction, then that means that our assumption that the measurement of angle 4 was less than the measurement of angle 1 is false. And if it's false, then it must be that the original conclusion was true. And that is your proof for that guy. So now we have this last example for you. And once you have done this example, this do-it-yourself question, then you will have completed your notes for this lesson. And I will see you in class. And thank you for watching.